After the detector, we have last part, that is a recorder where the actual IR spectrum is visualized. So IR spectrum is basically a plot of transmitted or absorbed frequencies versus intensity of the transmission or absorption. Frequencies appear in X-rays, x-axis in units of inverse centimeter, that is wave number, and the intensities are plotted on the y-axis in percentage units. IR spectrum in the transmission mode. So this is the most common use representation and one found in most chemistry and spectroscopic textbooks and reference books. In the IR spectrum or plot, we observe many peaks of different shapes, sizes and heights. So we can classify these peaks or bands such as the smaller ones called the weak band, medium size band, and the larger ones called a strong band, which is represented by, strong one is represented by the abbreviation S, medium by M, weak by W. Infrared shapes come in various forms. Two of the most common are narrow and broad. Narrow are thin and pointed like a dagger that we have just seen in the previous slide. So this is the narrow one. Broad bands are wide and smoother. A typical example of a broadband is displayed by the OH bonds, such as those found in alcohols, phenols, and carboxylic acids. So you can see in the present slide. Let's have a look about the various bonds, that is a covalent bond, because mostly we are going to deal with the covalent bonds that exist in the organic compounds. So let's have a look of carbon-carbon, then carbon-oxygen and carbon-nitrogen. So these all are IR active bonds. Not all covalent bonds display bands in the IR regions. Only polar bonds do so. So polar bonds, that means those have the electronegativity difference. So intensity of the bands depends on the magnitude of the dipole moment associated with the bond in question. Strongly polar bonds such as carbonyl bonds produce strong bands. Medium polarity bonds and unsymmetric bonds produce medium. Weakly polar and symmetric bonds produce weak or non-observable bands. So these are the examples, or we can say these are the various functional groups. So based on their electronegativity difference, or rather the polarity, they can have weak, medium or strong type of bonds. Now let's have the more information about the IR spectroscopy. Unlike other spectroscopic technique, IR spectra too provides good amount of information, basically the presence or absence of specific functional group. IR can provide a molecular fingerprint that can be used when comparing samples. If two pure samples display the same IR spectrum, it can be argued that they are the same compound or they have the same type of functional group. IR does not provide detailed information or proof of molecular formula or structure. It provides information on molecular fragments, that is specifically the functional group as we discussed in our previous slides. Therefore, it is very limited in scope and must be used in conjunction with other techniques to provide a more complete picture of the molecular structure. So these are actually some of the limitations that we are unable to reach to the final structure with the help of only IR spectra. Now let's have a look about the characteristics of the IR spectroscopy. The absorption of IR radiation by a molecule causes changes in their vibrational and rotational levels, and hence IR spectroscopy is also known as vibrational rotational spectroscopy. So as we have discussed, the atoms in a molecule do not remain fixed at certain positions, and that's why we have the various stretching and bending type of frequencies. So the two nuclei can vibrate backwards and forwards or towards and away from each other around an average position. So there are two types of fundamental vibration, that is the stretching and bending. The stretching vibration, it involves rhythmic movement along a bond with a subsequent increase or decreasing bond length. That is, if it is symmetrical, then they have the same length. That is, similarly on same side they will increase, on same side they will decrease. And if it is unsymmetrical, then there will be unequal increase or decrease in bond length. Basically, all the bonds in a molecule are not capable of absorbing IR radiation, but only those bonds which are accompanied by a bond change in a dipole moment will absorb in IR region. Further, the vibrations which are associated with the change in the dipole moment of a molecule are called IR active transitions. Those do not have any change, those are said to be IR inactive. Generally, the larger the change in the dipole moment, the greater is the intensity of absorption. Hence, the vibrational bands in simple hydrocarbons like methane, ethane, propane are very weak, while bands associated with bonds connecting atoms with electronegativity, that is carbonyl or nitrile, give strong bands. Now let's have the look about the transmittance. Transmittance is the ratio of the intensity of the incident IR radiation and the intensity of the radiation emerging from the sample. Absorption and transmittance are related by the equation A equal to log of 1 by T to the base 10, where A is the absorption and T is the transmittance. As the absorbance increases, transmittance decreases and vice. Now let's have the details about the applications. The main benefit of this technique is that some of the applications of IR, that is the main, is the functional group identification, or also we can call as a structural elucidation. The organic compounds can be established with the help of the IR range between 1400 to 1900, where we can identify the structure of some of the functional group like carbonyl, of aldehyde, ketone, ester. A study of the progress of reaction. So basically, IR spectroscopy is quite useful for studying the rate and progress of a chemical reaction. For example, The reduction of ketone to secondary alcohol can be detected easily as the absorption band of ketone is observed at about 1710 centimeter inverse. So this peak disappears when the ketone carbonyl is reduced to secondary alcohol. Detection of impurities. IR is also useful in the detection of impurity in a compound by comparing its spectrum with the spectrum of the authentic sample of the compound. A pure sample always consists of sharp peaks and bands, while the impure sample will have poor bands with some additional bands. Quantitative analysis. The quantitative analysis of an organic mixture can be done by measuring the intensities of the absorption bands of each component and by knowing the optical density of the absorption bands for the pure substance. Distinction between two types of hydrogen bonding. So IR can also be detect the presence of hydrogen bonding as well as the type of hydrogen bonding like intermolecular or intramolecular. Study of complex formation. So IR is not restricted to just functional group, but it can be useful in prediction of structure of complex molecule like penicillin. So there are two possibilities for a penicillin structure: alpha lactam and oxazolone. IR absorption bands confirmed the penicillin structure as the alpha lactam and ruled out oxazolone structure as alpha lactam and penicillium both show strong band at 1770 centimeter inverse. The most important application is in the forensic analysis and crime investigation. IR spectroscopy is useful in prediction of unknown compound and in presence of certain functional groups. Hence, this type of spectroscopy method is quite beneficial in forensic analysis. It plays an important role in crime investigation by locating the criminal offenders. Now let's have a look about the chemical identification of nanoscale sample contamination with nano-FTIR. So this is a demonstration about the identification of the sample that shows the topography image of scratched PMMA, that is polymethyl methacrylate film on silicon substrate, revealing a particle-like feature at a PMMA edge, which is mechanical AFM phase image that exhibits the strong phase contrast of about 70 degree. Each phase contrast indicate different materials. Without prior knowledge, however, we cannot identify the particle-like feature of about 100 nanometer diameter. By taking a nano FTIR absorption spectrum in the center of the particle, that is marked with P4, we find a significant different spectral signature compared to the spectrum taken on the PMMA film at the position marked with P3. While the latter exhibits the known PMMA vibrational fingerprint, we find that P4 a strong and broad peak centered around 1100 centimeter inverse, a sharp peak at 1260 centimeter inverse, and a small peak at 1040 centimeter inverse. So with the help of conventional FTIR from literature, we can assign the peak around 1260 centimeter inverse to the silicon methyl symmetric deformation, and the broad peak around 1100 centimeter, as well as the peak around 1040 centimeter to silicon oxygen, silicon that is disiloxane asymmetric stretching bonds. The appearance of these spectral lines is typical for the PDMS, that is polydimethyl siloxane. We can thus identify the particle-like features as a PDMS contamination. We note that PMA sample preparation and the pre-characterization involve PDMS material, obviously leaving PDMS, that is polydimethyl siloxane, reminders on the sample surface. Thus, we come to an end of this IR spectroscopy. Hope you come to know about the basics of IR, its principle, characterization and application. Let's have the hands-on training of the actual synthesis of the nanomaterials and its analysis using IR spectrometer. Thank you all the students and the participant for actively participating and attending this add-on course that is based on various spectroscopic technique. Thank you.